Chemistry, and you are watching Damn Science.
In this video, we'll discuss the question paper 5153 of the 9701 Chemistry Examination Series October-November 2023. So let's start directly with question 1 without wasting any time, and the question says the concentration of dissolved oxygen in a sample of water can be measured using the following method. Now what's the method? Manganese 2 hydroxide, that is MnOH twice, is oxidized by the oxygen dissolved in a sample of water to form manganese 3 hydroxide, that is the MnOH twice changes to MnOH thrice. So the oxidation number of manganese increases from 2 to 3. So it gets oxidized, and that is done by the oxygen dissolved in a sample of water. And this is how we are going to calculate the concentration of dissolved oxygen in a sample of water. And here is the reaction given, that how is MnOH twice reacts with oxygen to form MnOH thrice. And the manganese 3 hydroxide then reacts with the iodide ions to produce aqueous iodine. So here is again the reaction given, and the amount of iodine produced is proportional to the amount of dissolved oxygen. So you can see here that the iodine produced is directly proportional to the oxygen, because the oxygen used here will produce MnOH thrice, and that is going to form iodine. So higher the concentration of oxygen, higher the amount of iodine formed. And 25 centimeter cube of this solution containing aqueous iodine is transferred into a conical flask and titrated with against 1 into 10 power minus 3 mole per dm cube sodium thiosulfate Na2S2O3. And here again the reaction is given. Now let's go ahead with the tabular column which is given here. Here says question, sub-question A1 says complete table 1.1 to determine the mean titer to be used in calculating the concentration of dissolved oxygen. So here are the titers given, and we are supposed to calculate the mean titer to use it further for the calculation of concentration of oxygen. So here are the final burette reading given for the 4 titrations done. Initial burette reading for the remaining of again the 4 titrations. So we are supposed to find out the titer, that is subtract these two initial and final readings to find out the titer. So here we can say directly it's 27.30. Here again we can say it is 27.00. The third titer is 26.70, and the fourth titer is 26.80. Now we can see that there is a huge difference between the first and the second titer, that is the difference of 0.30. Again there is a huge difference between the second and third titer also, and again because here again it's a difference of 0.3, and here you can say the difference is of only 0.1. Whenever we are considering the titers, the difference should not be exceeding 0.10 centimeter cube. These readings are called concordant readings, and these readings are only to be considered for the calculation, to be considered for calculating the mean also. So if you calculate the mean of these two, only these two should be considered for calculating the mean, because the difference is only 0.1. So if I show the calculation, I'll be writing it as 26.70 plus 26.80. I can rub all this as I have rubbed. Now I can write 26.80 divide by 2, and so my answer should be 26.75. So this is the mean titer I have calculated from the table. Now let's go ahead with the further calculation, where it says calculate the concentration of dissolved oxygen in 25 centimeter cube of the solution. Show your working. Now here we are supposed to calculate only for the 25 centimeter cube of solution, because that's the volume we have taken for titration. You can see here we have taken just the 25 centimeter cube for titration. So if the concentration is given here 1 into 10 power minus 3 and the mean which we have taken is 26.75, so first we can calculate the moles of sodium thiosulfate, mole of sodium thiosulfate, Na2S2O3. Now let me first clearly find out something here. See, if we find out the moles of sodium thiosulfate here, we can see that the moles of iodine, that is moles of iodine, is half the moles of sodium thiosulfate, because the ratio here is 2:1. So again, if we calculate the ratio, the iodine which is produced in the earlier reaction is used here. So if we calculate the moles of MnOH thrice, we can see that compared to iodine, the moles of MnOH thrice is double. So from this you can directly say that the moles of sodium thiosulfate is equal to the moles of MnOH thrice, that is manganese 3 hydroxide. So what I'm going to do is write directly here the moles of sodium thiosulfate is equal to the moles of manganese 3 hydroxide, and that is equal to concentration multiplied by volume, and the concentration is 1 into 10 power minus 3, as we have already seen in the question, and the volume which we have calculated here is 26.75 again into 10 power minus 3, because that is in centimeter cube, and while calculating the volume of the moles we need to convert it into dm cube. So this is dm cube conversion. So from this I can directly write it is 2.675 into 10 power minus 5 moles of manganese hydroxide. Now again, if we compare the moles of manganese 3 hydroxide and oxygen here in the first reaction, we can see that manganese 3 hydroxide has a ratio of 4 and oxygen is 1. So 1:4 ratio. So you can see that the moles of oxygen is equal to the moles of manganese 3 hydroxide, that is 2.675 into 10 power minus 5 divided by 4 I should write. And now if these are the moles, so for calculating the concentration I should have moles divided by volume. So if the moles is this 2.675 into 10 power minus 5 divided by 4, these are the moles, and the volume again used is 25 centimeter cube if we remember. So 25 into 10 power minus 3 I'll say, because again we need to change it into dm cube. So if we do all this calculation, at the end we get an answer of 2.675 into 10 power minus 4. That is the answer we'll get. So the concentration is 2.675 into 10 power minus 4 moles per dm cube. This is the concentration. I hope the calculation is very clear. From the equation 3 and equation 2, we concluded that the moles of sodium thiosulfate is equal to the moles of manganese 3 hydroxide. So we calculated the moles is equal to concentration into volume. The concentration we have used is the concentration of sodium thiosulfate, and the volume which we have calculated here by the mean calculation. So we got the moles of manganese 3 hydroxide. From the manganese 3 hydroxide we can calculate the moles of oxygen. As the ratio was 1:4, we need to divide the moles of manganese 3 oxide by 4 to calculate the moles of oxygen. And now to calculate the concentration of oxygen, we have the formula moles divided by volume. So we have done moles divided by the volume, that is 25 centimeter cube. So 25 into 10 power minus 3 for conversion into dm cube, and finally we got this answer as 2.675 into 10 power minus 4 moles per dm cube. So that was sub-question A. Now if we go ahead with sub-question B, it says suggest a suitable piece of apparatus for the transfer of 25 centimeter cube of solution containing aqueous iodine. Now simple titration whenever we carry out, and if you want to transfer a particular volume of any solution, we directly use as volumetric pipette. Volumetric pipette is the apparatus we generally use to transfer a typical some specific volume of solution into conical flask. So volumetric pipette is the answer. Obviously the you can say the volume capacity is 25 centimeter cube, but that you don't need to specify, you just have to write the piece of apparatus name. Now here water samples are collected in a full sealed flask. Explain why the sealed flasks must be completely full. Now again, let's understand the procedure. What we had done is that we are trying to calculate the concentration of oxygen dissolved in water with the help of manganese hydroxide, manganese 2 hydroxide. So we want to find out the concentration of dissolved oxygen in water. And because of that, we cannot allow the oxygen from the air to react with manganese hydroxide, and that's the reason we don't want any oxygen from the air to react, and that's why we are keeping the flask fully filled with water and that also sealed. So the reason is that oxygen from the air, now you cannot write O2, we always need to write the spelling. Oxygen from the air should not react with manganese 2 hydroxide, and that's the reason that we keep the sealed flask fully filled with water. Okay, so that's the reason that we keep it this way. Now let's go ahead with the next sub question. Here it says the concentration of oxygen in water at different temperature is shown in table 1.2. The concentration values is missing for 25 degrees Celsius. So here are all the temperature given and the concentration of oxygen in 10 power minus 4 mole per dm cube shown. So that shows that at temperature 0, the concentration of oxygen in the water will be 4.58 into 10 power minus 4 moles per dm cube. So this is all the value given here. And if we go ahead with the next question, here it says plot a graph of concentration of oxygen against temperature on the grid. Use a cross to plot each data point. Draw a smooth curve of best fit. Now what I'm going to do is pause the video, complete the graph with the points and the curve, and then I'll come back. So here I have plotted the points with crosses as shown here, and then I've tried to draw a smooth line, but as you know, my digital pen won't give me a very smooth line, so it's gone little here and there. But with pencil and eraser you can always draw a very smooth line. Here is a curve, you can always see that it's a curve. So let's go ahead with the next sub questions. So the sub question 2 says use the graph to deduce the concentration of oxygen at 25 degrees Celsius. So let's go ahead, find out that at 25 degrees Celsius it's approximately, you can say it's 2.5. So if we plot here with a scale, you have to plot 2.5, but then with 25 it's little going above that. So if you find out from there, so here we will get our line. The line will be 1 mark above 2.5. You have to draw this with the help of a scale, which I don't have here. So from this, if you make out at 25 degrees Celsius, so you can write it is 2.55 approximately into 10 power minus 4. Don't forget writing 10 power minus 4 because that's given in the table itself. So 2.55 into 10 power minus 4 moles per dm cube is a concentration which we deduced from the graph, the plot which we have plotted on the grid. Okay, it says circle the most anomalous point on the graph. Suggest an explanation for this anomaly. Assume that there was no error in measuring the oxygen concentration. So if we find out the most anomaly, you can see here this is the anomaly, this is what we have plotted. So you can say that at temperature 10, we have found the anomaly. So we have circled this, that is the anomaly on temperature 10 degrees Celsius. So again, if I look at the point, I would say that the concentration of oxygen was measured lower. That shows that the temperature was not actually 10, but the temperature measured was greater than 10 degrees Celsius. So right, because as the concentration has gone much lower, so because of that I'll write the temperature used or measured, the temperature measured was greater than 10 degree Celsius. So the concentration at which the temperature at which the concentration was measured was not actually 10 degrees Celsius, it was greater. That's why the concentration of oxygen decreased. Now, why do we come to that conclusion? Because we noticed that as the temperature increases, the concentration of oxygen keeps on decreasing. So here, if the 10 degrees Celsius concentration is lower than expected, that shows that the temperature would have gone higher than 10 degree. That's why the concentration decreased. That's why the reason which we have mentioned here is temperature measured, temperature used was greater than 10 degrees Celsius, and that's why we got this anomaly. Now here is the end of question 1. Let's go ahead with question 2. Now let's start with question 2. Question 2 says benzene diazonium chloride, that is C6H5N2Cl, decomposes in water as shown in the following equation. And here is the equation where it shows that it reacts with water and forms an phenol, nitrogen gas and hydrochloric acid in the aqueous form. A solution of 0.0750 mole per dm cube benzene diazonium chloride decomposes at a constant temperature of 50 degrees Celsius. Now it's mentioned that the temperature has to be maintained at 50 degrees. It has to be constant throughout the reaction. The volume of nitrogen gas N2 collected is recorded every 5 minutes for 45 minutes. So every 5 minutes the volume of the gas nitrogen is recorded. The sub question A says draw a labeled diagram to show how the apparatus could be set up to carry out this experiment. So we have to show the setup of an apparatus which could be used to collect the volume of nitrogen gas, and it has to be recorded every 5 minutes. So volume is recorded every 5 minutes and we are going to collect nitrogen gas in an apparatus. So this is how we are going to set up. So if we are going to collect the nitrogen gas, obviously the reaction mixture has to be carried out in a sealed container. Then only the gas can be collected in a specific way. So if we are collecting say gas in gas syringe, then the reaction has to be carried out in a sealed conical flask. So here we are setting up conical flask in a sealed way, and from the seal we are passing a tube which will get connected to a gas syringe. So if a gas syringe is connected to such a tube, delivery tube, it's going to collect the nitrogen gas. So this is a gas syringe. Now if we are measuring the volume of gas, obviously this gas syringe has to be graduated. So here we are showing the graduation on the gas syringe also. And this is the reaction mixture. So we should label it. It's written, draw a labeled diagram. So we need to label it conical flask mentioned in the apparatus. This one is a gas syringe, and you can also mention here a cork, or you can also write any substance which can seal the container. Here it's a glass tube, you can mention here it's a glass tube. This is label. Reaction mixture, you don't need to label, but just being on the safe side, I'm writing reaction mixture. Now one more thing here is needed, that the temperature has to remain constant at 50 degrees. So we need something which can maintain the temperature at 50 degrees. So we need to mention here a electrically apparatus which can maintain the temperature Now this is called thermostatically controlled water bath. This is called thermostatically controlled water bath because that's a special apparatus in which the temperature of the water can be maintained at any given temperature we wish. So I'm drawing a thermostatically controlled water bath. So we need to draw a water also around it. So this is thermostatically controlled water bath. This is how we are going to show an apparatus. We have labeled it all properly. We have shown the water bath to maintain the temperature. We have shown the conical flask which can be sealed to collect the volume of gas. And we have shown gas syringe which can measure the volume of gas. So I think this is how we can draw a diagram. This carries 3 marks. Let's go ahead with question 2. Question 2B part. Using this method, a student obtains the graph as shown in figure 2.1. So here is a graph where it shows a curved line joining all the points where volume of nitrogen gas measured in centimeter cube is labeled on y-axis and on x-axis is the time in minutes, right from 0 to 45 minutes because that's how the volume of gas is measured. So here is a curve. And it says on figure 2.1, draw a tangent to the curve at t is equal to 0 minutes. Calculate the initial rate of reaction in centimeter cube per minute. So we need to draw a tangent at 0 minutes. So here is 0 minutes and we should draw a tangent at this point. Tangent is a point which just touches this line. So if we draw a tangent, now you can see that I've taken a graph grid on a very small scale and I have drawn a blue tangent. You can see there is a blue tangent which I have drawn with a straight line just touching the point at 0 minutes, and we should draw this tangent big enough. This tangent is big enough, long enough of approximately 2 to 3 centimeter because it's easy to measure the coordinates at x-axis and y-axis, and that's how you're going to find out the gradient of the slope. So you can see that I have taken 2 points. One of the point is touching approximately 6 minutes on x-axis and then 30 centimeter cube on y-axis. So this is how we're going to take the gradient. So gradient from on x-axis is 0 to 6 minutes, and on y-axis the gradient for the 2 points which we are taking for y-axis, that is y2 minus y1, is 30 and 0, so 0 to 30. So let's calculate the gradient for it now. So if we calculate the gradient, that's going to be y2 minus y1 upon x2 minus x1. Now we knew that it's 30 minus 0 upon 6 minus 0, and we get the answer as 5.00 centimeter cube per minute. That's how we calculated the gradient, and that's the initial rate of the reaction. That is, the gradient of the slope is going to be the initial rate. So we have drawn a tangent at the initial point 0 minutes, calculate the gradient for the tangent, and that gave us the initial rate. Now let's go ahead with the sub question 2. Let's go back to our normal size so that we can read the questions properly. And here is the sub question 2. It says explain why the initial rate of reaction is calculated at t is equal to 0 minutes rather than dividing the total volume of gas produced by the time taken to produce it. Now the reason for this is that the rate is not constant throughout the reaction, it's decreasing, and if we calculate the rate by dividing the total volume by total time, it's going to give us the average rate. So average rate we don't want to calculate, so we can write that the rate of reaction is not constant, throughout the reaction, and the total volume of gas by time gives us the average rate, gives us the average rate. But the thing is that we wanted the initial rate only, average rate we didn't want. So we can't do that. We have to calculate the gradient at the initial point if we want to find out the initial rate. The sub question 3 says, describe how the curve in figure 2.1 would be different, if at all, if the atmospheric pressure increases, all other conditions stays the same. Let's first understand what's happening. They're asking what will happen if the atmospheric pressure is increased. Atmospheric pressure is increased. Let's have a look at the reaction again. What is happening in the reaction here? You can see that there is a gas on the product side, and if the atmospheric pressure is increased, the gas won't be produced very easily, or you can say the gas production, the rate of production of gas will decrease. So the rate of reaction will also decrease, and in that case, if they have asked us a question that what would happen to the curve, then we can say that the curve would be below the line, or I should say the new curve would be lower or below the original curve, because the rate of production of nitrogen gas would go low because of the increase in the pressure. Okay, the fourth sub question says, on figure 2.1, draw a second curve to show the graph produced in the same volume of 0.375 moles per DMQ C6H5N2, that is benzene diazonium chloride decomposes at a constant temperature of 50 degrees. All other conditions stays the same. Now if we look at the concentration used earlier, the concentration used earlier was 0.075, and now if we are using 0.375, that is half of the concentration used earlier. In this case, I would say that the total volume of gas produced should also go half, because if the concentration is half, the nitrogen gas which is produced from diazonium chloride would also go half. So if we draw a curve below this, so here is our original curve, and let's try to draw a curve, second curve on this. Here we can see that approximately 55 centimeter cube of gas is produced in overall 45 minutes. So if the concentration is decreased to half, then the 27.5 centimeter cube volume of gas should be produced here. So you can see I have drawn a mark here to show that is the 27.5 centimeter cube of nitrogen gas. That is the total volume of gas produced. So it should end up here. The curve should end up here, and it should almost go half the earlier curve. So I'm trying to draw a curve which is going exactly half the earlier volume. So here we draw the curve, and let's draw a smooth curve. I've gone a little above, so the curve should go little down than what I was trying to draw here. So this is how the curve should go, exactly half the volume of the gas produced over 45 minutes, and try to draw exactly half of the other points which are already shown here on the grid. So this is how the curve would go with half the concentration. Let's go ahead with the next sub question C, where it says another student investigates the effect of changing the concentration of benzene diazonium chloride at 50 degrees Celsius. What is it trying to change? Changing the concentration. Where it says in the sub question C, it says another student investigates the effect of changing the concentration of benzene diazonium chloride at 50 degrees Celsius. So this time the temperature is not changed, the concentration is changed, and he measures the time taken to collect 0.015 dm cube of nitrogen and calculates the rate of nitrogen production by dividing 0.015 dm cube by the time taken. The results are shown in table 2.1. So here are the results where the concentration is shown and the time taken to collect 0.015 dm cube of nitrogen gas in seconds given. So we are supposed to calculate the rate. If we want to calculate the rate, how are we going to calculate the rate? The rate is equal to any change, that is change in the volume or change in the amount of product or change in the amount of reactant divided by time, we see. So what is the change in the product here? We are collecting 0.015 dm cube, so that is the change in the product. So amount of product is 0.015 divided by the time taken every time. So if we calculate that, so we are supposed to calculate the production of nitrogen gas divided by the time taken to produce it. We need to divide the time here. Say the first reading should be 0.015 divided by its time 21. This is how we are going to calculate the rate. So if we read the sub question, it says complete the table to calculate the values for the rate of nitrogen production and give your answers to three significant figures. So if we write three significance, keep on dividing 0.015 divided by the time. The first answer we get is 7.14 into 10 power minus 4. Now I am writing the answer to three significant figures. So if I keep on doing that, the next answer is 4.55 into 10 power minus 4 again. The next again, if we write, it is 3.13 into 10 power minus 4. It is 3.13. Here 2.34 into 10 power minus 4, and the last one is 1.23 into 10 power minus 4 again. So this is how we got the readings and we completed the table. If we go ahead with the next sub question, says the reaction is first order and obeys the following rate equation. The rate is equal to constant rate, constant K, into the concentration of benzene diazoxide chloride. And you can see the reaction is first order because the power of this concentration is 1. Explain how the data in the table 2.1 supports this statement. Now if we look at the table here, you can see that the difference between the first two readings, you can say that the concentration was decreased by say it's 1.25 times. It's decreasing by 1.25 times. The concentration is decreasing by 1.25 times from 0.5 to 0.4. Now if you calculate the ratio of the rate by which it's decreasing, again you will be able to see that it's decreasing by again same 1.25 times. So if the change in the concentration is directly proportional to the change in the rate, that is with the same ratio it decreases, or with the same ratio the rate increases, then it is first order. So let's write the same explanation here, that comparing experiment 1 and 2, comparing experiments 1 and 2, the concentration decreases by 1.25 times, and the rate also decreases from, I'll just write the value 7.14 into 10 power minus 4 to 4.55 into 10 power minus 4, which is 1.25 times. That's why it is first order. Okay, let's go ahead with the step sub question 3. I think you understood that what had we written in the 2, that the ratio by which the concentration of any experiment increases or decreases, with the same ratio the rate also should increase and decrease, then it's the first order. So here we have proved that. Okay, let's go ahead with the sub question 3. It says state the dependent variable in this investigation. Now what is a dependent variable? Dependent variable is something which we measure during the experiment, and independent variable is something which we change. So here what had we changed in this experiment? We had changed the concentration, so that was independent variable. Dependent variable is what we measure. So what did we measure here? We measured the time. time taken to produce a specific volume of nitrogen gas that we measured. You can see in the table what did we measure for producing 0.015 nitrogen gas in dm cube. So we measured time in seconds to collect that. So time is the dependent variable. Let's go ahead with the fourth sub question, where it says the student wants to perform a similar experiment using 0.2 mole per dm cube benzene diazonium chloride. Describe how the student should make a standard solution of 100 centimeter cube of 0.2 moles per dm cube benzene diazonium chloride starting from a solution of 0.5 mole per dm cube. Give the name and size of any key apparatus which should be used and describe how the student should ensure the volume is exactly 100 centimeter cube. Write your answers using a series of numbered steps. Now let's first start with the calculation, how to calculate the volume of 0.5 concentration to be taken to change it into 0.2. That's why we are decreasing. Now with what ratio are we decreasing, that we can calculate. But if I teach you a simple calculation that if we are using 100 centimeter solution, we are going to make 100 centimeter cube solution that's given in the question, and if we are using 0.5 moles per dm cube concentration, we want to change it into 0.2 moles per dm cube concentration, then how much of the volume should we take? That's the simple cross multiplication I would say you will be doing. So your answer should have 100 into 0.2 divided by 0.5. That's how you're going to calculate. If you calculate, you'll get 40. So 40 centimeter cube volume you should use to change it into 0.2 in 100 centimeter cube any container. So how are you going to do? Now let me explain. We have done the calculation that how much of 0.5 mole per dm cube concentration volume we will take, and we will dilute it to 100 centimeter cube to change it into 0.2 moles per dm cube concentration. Okay, so if we are measuring 40 centimeter cube, we can't use pipette because pipette have generally the highest capacity of 25. So you can use burette. So what we can do is measure, starting with the first step, measure 40 centimeter cube of 0.5 mole per dm cube, 0.5 mole per dm cube of benzene diazonium chloride, 0.5 moles of benzene diazonium chloride. Let me write that fully. Okay, and or we can say that, okay, measure, and yeah, I'm writing it in the next step, that transfer this solution, transfer this solution in 100 centimeter cube volumetric flask, 100 centimeter cube volumetric flask. Now I'm mentioning 100 centimeter cube of volumetric flask. Volumetric flask is a flask which is generally used to measure, prepare a standard solution, and so we have various capacity of volumetric flask here, like 100, 250, we have 500 centimeter cube, we have 1 dm cube also. So here we are using 100 centimeter cube volumetric flask. So transfer this solution in 100 centimeter cube of volumetric flask and dilute it up to the mark, with distilled water. Now specify distilled water because that is very important. Distilled water has to be used, only distilled water has to be used to make a solution. So dilute it up to the mark with distilled water and shake well. So this is how we are going to make the solution. So first important step is calculate the volume to be used to make that solution. Specify all the apparatus we using, so we can write yes, measure 40 centimeter cube of this with the help of burette, with the help of burette. This is also important. We should use burette and we should specify this. So we are specifying it with the help of burette. Here we are specifying volumetric flask, and we are specifying distilled water and shake well. So this is how we are calculating and describing the steps to make a solution. Next sub question, explain why 4 must be carried out at a temperature below 5 degrees Celsius. Now, as I said, benzene diazonium chloride decomposes above the temperature of 5 degrees Celsius. So we can specify here that above 5 degrees Celsius, actually it's 10 degrees Celsius, above 10 degrees Celsius is discussing, but we always keep a safe temperature of 5 degrees. So above 5 degrees, benzene diazonium chloride decomposes, and if it decomposes, what happens? The concentration changes. That's how we are going to specify here. Now let's go ahead with the next and last sub question. D says benzene diazonium chloride is used in the manufacture of synthetic dyes. A student prepares a sample of dye using the reaction scheme shown here in figure 2.2. You can always pause the video and have a look what's happening. Phenylamine is changing to benzene diazonium chloride, and that is again, this is called a coupling reaction, where a benzene diazonium chloride is bonded to one more compound, phenylamine, to make another compound. So in step 1, phenylamine is converted to benzene diazonium chloride, and then it's again reacted with phenylamine to produce a solid dye, which is then filtered. So first the dye is produced by a reaction and then it is filtered. The students' final yield is 52%. They had not spilled any reagents or products. Suggest 2 reasons why the students' yield was lower than 100%, and assume no more errors were made in the measurements of any substances. Now, so the most important reason here you can write is that the benzene diazonium chloride might decompose. That is the most common reason, might decompose, or it might react with water. So that is the first reason. And the second reason may be that during the filtration some dye is left over, in the filter paper, or you can give any such valid reason where it says that there had been some loss during the reaction, or it has reacted with something else, or it has been wasted in some transport while passing from one substance to other. It's not spilled, but it may stick and get wasted. So but then you need to specify it very clearly that what has happened, the way we have mentioned here, that it might have been left over in the filter paper. I should specify here filter paper. Okay, let's go ahead with the last sub question. Explain why the solid dye should be dried before assessing the melting point. Okay, if we are assessing the melting point, the substance should be fully pure. If water is there, then water might change the melting point. So what I'll write is that the presence of water might change the melting point, the actual melting point. So that's why we need to ensure that all the water has been evaporated to get the exact melting point. So here we have ended up with this whole paper 5.1. I hope it's very clear.